So what happens here so again, it's not difficult to see that T maps to E T like that, so to the field. This is a Markov process. This is a Markov process with continuous path on this omega. I call it omega as there, but it's a different object. So it's a Markov process. Here you need some analysis.
Respect to what filtration here?
Its own filtration. So I just define it as going on, and
because
so
it depends on the path of X.
yeah, but the path is included. So mind that eta contains the actual profile. So if I tell you the actual profile, then no matter how it was built up, what comes in the future has a distribution condition on that. What is more surprising is that I can identify a very neat and a very pretty stationary measure to it. So I define a measure, pi will be a probability, a Gaussian probability on omega, which I'm going to define now, namely with zero mean, or let me kx. Let me denote by these the expectation with respect to, so integral according to pi. So zero mean, Gaussians, I tell you the covariance field, omega k x omega L y expectation equals, I'm sorry I have to continue like this because blackboard I write too big letters for these can you see what's written there? No, I have to write it again. So omega k x omega L y equals minus d sub kl, this is partial differential, I will give you a function in a moment, of what? Of Green's function, sorry, Green's function is not good to differentiate, give me a second not to make mistakes here. Yeah. V convolved with Green's function x y minus x. Is it clear what I mean by that? Take V, convolve it with the Green function, with the Green function, and what you get, differentiate doubly, take second derivative KL. I give you, call this function k sub k and L y minus x. I give you the Fourier transform. That's the not good joke. The Fourier transform of k, which is easier maybe. Can you see this one? The Fourier transform will be, you can guess it from the previous one, P sub k times P sub L right? So this is a decent covariance structure. And mind that I said at the very beginning that I need that my V be such that its Fourier transform be non-negative. And here is why. Because this formula makes only sense as a covariance only if this guy is positive. And this gives rise to a very decent, due to my conditions on the function phi, this v sub p, the v sub p, v hat p behaves like that. So v hat p behaves like that. Right? Decays fast due to infinite differentiability of v. It's bounded due to exponential decay of v, and has positive. So this is the behavior, or this is the Fourier transform of an approximate delta. Right? So this guy you see here is a decent covariance function, or Fourier transform of a decent covariance matrix, and I define the measure pi be the Gaussian measure on this omega, which has these covariances. This Gaussian measure will be concentrated on that space, easy to see. So I have a probability space, a decent probability space. I will put myself, yes, why do I have this? Because the statement is the following: by some miracle, can you see this or not? Yes, you could. By some miracle, this pi is stationary and ergodic. The ergodicity is the stationarity is the miracle for eta t. So eta t as a Markov process will have this measure say, indeed it's a miracle. So don't try to what happens is the following, a very subtle balance. So what happens, how does this eta change in time? It changes due to translation, because the random walk is moving, so it's translated due to, and also changes due to accumulation of local time. You accumulate local time, that's the derivative of the local time changes, but these are balanced in such a way, so it's such a sort of harmony between the two, that it makes this measure stationary. It's not a, once you guess, it's not so difficult to prove. I have two proofs of this statement. I will not show you the proof, but you'll find it in the paper. On omega, yeah. So capital omega is a space, capital omega is a space of gradients, of gradient functions. Space of fields which satisfy the gradient condition. It makes sense that a Gaussian measure is defined on it.
Yes, but then you have to specify covariance of, say, omega 1 of x and omega 2.
Exactly, that's written there. Omega k of x and omega l of y. For any x, y, k, and l.
No, let's say k is 1, suppose.
The k are the dimension coordinate, the coordinate indices.
No, let's say d.
Omega sub k. The omega is a gradient, it has d coordinates.
No, suppose d is 1.
So, suppose d is 1. If d is 1, then k, there is no k and l, then you have only 1. If d is 1, let's in one dimension, okay, let's understand what happens in one dimension. In one dimension, this omega, this makes sense. This is not a restriction, because in one dimension anything is a gradient. And here, k is only 1, doesn't make sense. M is not a multi-index but an index. So the space is the space of those functions. In one dimension, the space is the space of those functions. Let me put it in one dimension now. This is just a number now. So this is dm by dxm. So these are the seminorms. In plain words, don't look at the formula. In plain words, this means functions which are infinitely differentiable and all partials increase far slower than any power at infinity. Right? It makes sense. And now I define a measure on this space, a Gaussian measure on this space. So I take a Gaussian field, of these omegas such that their expectation is 0, and the covariance, now let's put this in one dimension, in 1D, omega k, omega L is, this is just D2. This is Gaussian here. This is okay, you have to understand what that means. I will explain it here in a moment. So this will be, right? So this is better to understand. The Fourier transform is, this is just 1 VP. So Gaussian field whose, so omega in one dimension is very simple actually, is the field, that Gaussian field on R1, we are in R1 now, such that the covariance is just VP. I can just write it down as an integral over white noise if you wish. Right, so actually what you will see, if you want it as an Ito integral, in 1D, actually I could do it in higher dimension too, but let's do it in 1D. This is a good question. In 1D, let's have U such that U convolve with U equals V, and I can do that because V Fourier transform of V was positive, right? And omega x is equal to integral U x minus y d wy, where dwy is the white noise. In 1D is simple. Probably I could write down formulas like that in higher dimension too, but you would need higher dimensional white noise. Did I answer your question? Yes?
Yeah, I is clear.
It's clear, yeah? And in higher dimension it's more complicated because it's a vector field. Good.
Omega equal to U convolves with omega. Is that right?
This is white noise. This is not the same, maybe notation is no good. This is the, okay, let me call it beta. Call it beta, and beta is a white noise. Good? Okay, let's go on. Now, indeed, let me just emphasize that this is absolutely not straightforward that this is true. Absolutely not straightforward that this is true. I have two proofs. One goes through Ito calculus, and the functional analytic one, which you may see later or not, depending on time. But this is a main thing, because otherwise I couldn't do anything. So that means, again, that I have, and I assume that my Markov process is initiated, or the initial distribution of the L of omega is like that, of eta is like that. So I put myself in the stationary case. So again, I take the Hilbert space, which is L2 of omega and pi, where omega is that function space, pi is this Gaussian measure. And mind that pi is essentially the distribution of gradient of Gaussian free field. Except for that local regularization, this is gradient of Gaussian free field. Right? So omega is gradient as a random object, is gradient of Gaussian free field in the corresponding dimension, locally regularized. Okay. And I will put myself in this Hilbert space, and all my analysis will be in this Hilbert space. Good. Now let's go on. this one moves much easier than the others. And that's why I bumped it all the way. So let's go back to our problem. In both cases, so one case is the random walk in random environment. The other case is the self-repelling Brownian polymer, and let me call it random walk in, this is not whatever random environment, divergence-free random environment. Divergence-free random environment, let me do it that way. In both cases, I have this displacement. Xt is the displacement of the random walker. Xt is the displacement of the random walker. And I want to decompose it. This is the most natural thing I'm doing. I decompose it as a martingale plus a compensator. So I define a martingale. MT. Let me put here M0T because I will have another martingale later. Be xt minus integral from 0 to t phi eta s ds. So what I mean by this, and you will see in a moment what it is. So I will be able to separate a martingale such that I subtract from the displacement the integral of a function, actually an element of that Hilbert space I just defined, integrated along the trajectory of the Markov process I just defined. Mind this phi is in RD, is a vector valued because everything is vector valued here. Where phi is omega to RD, so it's a function of the position of the state of my Markov process. And in the two cases, in the random walking random environment, recall I defined it already. I had phi of omega was sum over E, nearest neighbors, E times V sub E omega. So that's just the local drift. The actual local drift, if you subtract from dxt, you subtract this times dt, that will be a martingale increment. Right? In the other case, in the case of self-repelling Brownian polymer, let's see what is this phi. The Markov process, remember what the stochastic differential equation was. It was dxt was equal to dbt, I just write down what was already, was minus gradient of v convolve with lt at xt dt. Remember this? Sorry? I'm sorry, say it again. No, this is local. This is what it feels local. In order to keep it Markov, you have to record all the field, but it's pushed locally by what it's locally there. Right? So this is, so that makes that, let's integrate. We get xt, say x naught is 0, is bt plus, I write something, integral, exactly this form, just put it on the other hand, on the other side, where phi omega, so from here it follows that phi, write it down and you will convince yourself very easily. Phi of omega is an element of this function space now, Anybody wants to tell me what is that? No, this is integrated over time. So it's omega at 0. Omega is a vector field. Its value at the origin is your push. No, this is what you see here. This is phi. Okay, this is how should I put it? This is exactly omega. This is what you see here is omega. How should I put it? Yeah, it's eta t at t. Sorry, eta t at 0, exactly, sure. Eta t at 0. Yeah, you understood it because you corrected me. That's eta t at 0. So if that's eta t at 0, this is what I have to integrate here is phi omega equals, so this is the particular function which I have to integrate along, it looks like a simple function, but you integrate it along the trajectory of a complicated Markov process. Right? So let me just write this down again. So I have xt equals mt plus integral from 0 to t phi eta s ds. This is the same thing written again. When I told you very explicitly every element from here. So what I have to understand is how this guy behaves. Now this is a martingale with stationary increments, because everything is in a stationary regime, so the increments of this guy will be stationary. That's easy to see. That's a martingale with stationary increments. We know everything about this. In particular, we know that this guy behaves diffusively. I will be able to compute everything I want about this. Right? In order to understand the global behavior of xt, you have to understand the global behavior of this guy. Which is a difficult thing because integrating a function along the trajectory of a Markov process is a difficult object. You teach it for undergraduates when the Markov process is a finite state Markov chain. If it's a finite state Markov chain, still it's not a very trivial exercise to prove that this type of integral obeys the central limit theorem, but you can do it by various tricks. But when the Markov process is truly an infinite dimensional one, a difficult one, then it's a difficult thing. Right? And I have two different scopes. I want to understand in some cases diffusivity, and in some cases superdiffusivity. Right? In some cases I expect that this behaves diffusively, that means divided by square root of time I get a central limit theorem. Then of course I have to prove that this already yields a central limit theorem. I have to prove that this together, so this on its own yields a central limit theorem, and the two together yield a central limit theorem. On the other hand, in okay, let's see. So when diffusivity expected, if diffusive expected, then prove a good martingale approximation of this integral. A good martingale approximation of, and by a good martingale approximation I mean that prove a martingale approximation that will be m1 of t, such that this second martingale differs from this first one less than square root of t. So divided by square root of t, the two together yield the central limit theorem. Now this is the famous Kipnis-Varadan type of object. So a la Kipnis-Varadan. Not quite, but this is the catchword I have to say here. It's not just copying Kipnis-Varadan, of course, but that type of circle of ideas. Of course, again, it's It didn't start with Kipnis and Varadhan, but that's how we call it today, that Kipnis-Varadhan theory. This martingale is exactly about martingale approximation of additive functionals of Markov processes. If you can. In the other cases, if super diffusive behavior expected, then let's look at this. This guy is diffusive. So if super diffusivity happens, then it can happen only due to this. Then prove super diffusive bounds for the integral. So in both cases, you have to understand very well the behavior of this integral. These are two oppositely different things. In some case, depends on your problem, what is the case, which one is the case. Good. So we are in the Hilbert, and both will very much rely on down-to-earth functional analysis on the Hilbert spaces I gave you. So we will have to see some operators on those Hilbert spaces. We have to do some either spectral analysis or both spectral analysis and resolvent calculus on those Hilbert spaces. So let's go on. So I'm sure I won't have time. When did we start? 25. 25. According to that clock. So I'm, oh, okay, I have plenty of time. So let's go to the Hilbert space H. Go to H. Now H is two cases, so these are two Hilbert spaces I speak about. They are common because one is in the discrete random walk case, the other one is in the continuous. These are two different problems. Just there are lots of formal identities. So I have either H equals L2 of omega pi, where actually in the discrete case, in the random walk, in random environment case, remember I had omega, I don't write the filtrate, the sigma algebra, I had pi, I had tau z, z in zd, and L2 of this, and actually, let me put it somewhere, zero, I mean zero mean. I don't care about the constant functions, right? And in the self-repellent Brownian polymer case, I had omega pi. Remember omega, what was omega? These are denoted the same, but this was an abstract sort of omega with that action on it. And this was a very concretely given. Pi is that Gaussian measure I told you. And I didn't tell, but it's very natural that here, okay, again I have a stationary ergodic shift action because that Gaussian field is translation invariant to the ergodic. So I have tau z, but in this case, z is in Rd. So I didn't say this explicitly, but if you look at the form of that field, of that space omega, there is a natural shift action, and the measure is shift invariant and ergodic, that Gaussian measure I gave you. Right? Now, I'm in this space. I want to define some operators. Of course, you must forgive me if I don't give you all details, because these are long papers with lots of technical details, and I simply don't have time in 2 hours to tell you everything. Let me define some simple operators. I only will speak about the simple. Okay, in both cases, so what I'm heading for, in both cases, I have L, the infinitesimal generator of the semigroup of my Markov process. So better I write not in this way. I write a semigroup. In both cases, formally the same. I have expected value starting from omega of any function f at eta t is the semigroup acting on f. This is the semigroup acting on f, and this is PTF omega. This is the semigroup of my Markov process acting on this Hilbert space, right? And just to introduce notation, I write Pt equals e to the TL. By this I mean, but I denote by L the infinitesimal generator of the semigroup, right? Which will be typically an unbounded operator. By the way, L will be a bounded operator in this case because it just jumps with finite rates, and you write down L will be a bounded operator. The unboundedness of L is just a nuisance. It's not an essential thing. Okay, let me go a little bit ahead. Not the unboundedness of L is the difficult thing, but the fact that the inverse of L is unbounded, that you have no gap in the spectrum of L, right? So L is the infinitesimal generator, which it can be written down rather explicitly, and that's what I'm going to. And I do more than that. I want to separate L into a symmetric part and an anti-symmetric part. Formally, this means that L plus SL starred by 2 equals minus S. I write it minus because this S will be a self-adjoint positive semi-definite operator. That's why I put a minus here, because L is infinitesimal generator of a contraction semigroup. And A will be an anti-self-adjoint operator. Now, when L is unbounded, then you have to be a bit careful about all these things I tell you, but it makes sense what I'm saying. And I will write down explicitly the operators. Right? Now, let's go to these Hilbert spaces. And these Hilbert spaces H, it makes sense to speak about gradient in the discrete case. Let me put just 1 and 2, because otherwise I always have to write all these letters. In case 1, it makes sense to speak about gradient in the direction E. E is one of the unit vectors of f omega equals f of tau omega tau E omega minus f omega. This is a bounded operator, and you know everything about it. In the other case too, you have to be a bit more careful about, and this is for 2D vectors. It would be, you could survive only with D of them, but then you would lose some symmetry. Anyway, I prefer to define it like that. Is it clear what I mean? This is a unitary operator, this is unit, this is a unitary minus identity, it's a well-defined object, no problem. In the second case, I define according to the directions, because I have direction derivatives in the various directions. So I say here I could be, or maybe better k, not to confuse it, square root of minus 1. K goes from 1 to D, right? And you define it of f omega, you define it as limit as epsilon goes to 0 of epsilon to the minus 1 f epsilon tau I tau, how should I put it? Epsilon tau times tau E sub I omega minus f omega. Is it clear what I mean? It's continuous shifting, so you shift by a little bit in direction that, subtract what's there, divide by epsilon, and this is certainly not defined for all f's, because now we are in the realm of unbounded operator, but for many it's densely defined, and you can define it as an unbounded operator, no problem in definition, right? And similarly, so mind, when I write nabla and nabla, I don't mean derivatives of up in the space of function of Rk, but in the Hilbert space. I just use the same abuse notation, if you wish. And similarly, I can define Laplacian in both cases, and let me not do it, you will be able to define the Laplacian in terms of these operators. In both, Laplacian as acting on the space H. So these are operators acting on the space H. In the discrete space case, in the ZD case, these are bounded operators. In the RD case, these are unbounded operators, but don't have difficulties with defining them because this is actually ergodic element, or maybe not elementary, but in the realm of ergodic theory, what I'm saying now.
One point I didn't realize now that so this eta was not a reversible but has this stationary measure.
I'm sorry, I didn't.
That eta process is not reversible.
It's not reversible. That's okay. Maybe I didn't emphasize this. Yeah. If it was reversible, then I would take my hat now and go home because I would say that, okay, we understand everything about it. If eta t was reversible, then I wouldn't have anything to do. Right? It's not reversible, which is manifested in the fact that this A is non-zero. So that's my work in the last 10 years or more than 10 years is about understanding non-reversible cases of these problems. Actually, in the reversible case, you will never have super diffusivity.
So this environment process is usually never reversible, is it?
Say it again?
The environment process is usually never reversible, is that?
I don't know what is usually, what people are looking at is reversible usually. So, for example, random walk among random conductances, and that's about three quarters of literature about random walk in random environment is about random walk among random conductances. That's reversible, and that's why everything is done there, because it's reversible. What I'm looking at is non-reversible. So my main point is that non-reversible. Try to understand what happens in the non-reversible cases. Okay, and here is the Laplacian, which I will not write down definition, but given these, you can easily guess how to define the Laplacian in these cases. Now, it turns out that in the cases I discussed, the symmetric part is the Laplacian. I mean this Laplacian on H. So in my cases, S equals minus Laplacian. So Laplacian is negative semi-definite, and I prefer to write S, the symmetric part, as a positive semi-definite thing. Now let me make a parenthesis here. I don't give you the most general story, because time is short. So actually what I need, and this answers the question of Shiva from the very beginning, actually what so if I had 7 hours to speak instead of 2, then I would give you this full story, and actually what I need is S equals minus some constant, call it alpha, positive constant, times theta, plus say S1. So that means that S is minorized. So this could be whatever almost, but S should be, how should I put it? The symmetric part be a positive constant times the Laplacian plus something. This is an ellipticity condition. This is an ellipticity condition, and I need this ellipticity condition in all my stories, but I don't give you the whole story now. That's only technical. So just 1 second. So I will do it like that. I will do it like that, but just keep in mind that I can do more than that. And question?
I don't see how the spaces are coming in. It seems like a very general way of looking at it. RD and ZD are incidental, is that right?
RD and ZD, why are they incidental? Because our motion is in RD and ZD. So,
as long as you have a basis vectors, you can do this gradient.
But on ZD you can't do that, because on ZD you have just discrete shifts. On ZD you only have discrete shifts. On RD you can't live only with the discrete shifts, because your motion is continuous, right? And the Hilbert spaces are not incidental. I need it's very essential that I'm doing analysis in these Hilbert spaces. Ergodicity is essential. Ergodicity is absolutely essential. Ergodicity is, okay, let me not go into it. Ergodicity is equivalent. Ergodicity is equivalent, ergodicity of the shifts of those shift spaces is equivalent to saying that that 0 is a non-degenerate eigenvalue of this operator. That only the constant function belongs to the 0 eigenspace. As I factored out the constant function on my space, this doesn't have 0 eigenvalue. Right? If delta had a gap in its spectrum, so if my space would like that, this is again an error, then I would be done. But the point is about delta not being invertible, and all the problems come from there. Good. So S is minus delta. So let's keep that in mind. And you see what I said. And now, what to expect? Let's see what to expect. When I didn't tell you when to expect diffusivity, when to expect super diffusivity. No, I just gave you examples, but no intuition about why. What to expect? In order to say what to expect, I define a function of time. Let me call ET be the expectation of integral from 0 to t phi eta s ds squared, and mind that this is expectation not only over the process but the initial condition as well. So this is eta s is a stationary Markov process, so this is the stationary expectation. If you go to the random walking random environment problem, this will give you an annealed expectation, not a quenched one. It's not about fixing the environment, and with fixed environment compute what you compute, but anneal it, average over the environment too. So environment is also average. Initial, this is a stationary expectation, right? Now this is elementary computation, which I'm not, this is indeed elementary computation. These 3 dots denote elementary computations, and this will be actually twice integral from 0 to t of t minus s times expected value of phi eta 0 phi eta s, and what you see here is nothing more than computation done in the stationary regime using stationarity, nothing else. Only stationarity is used. I tried to guess which chokes are the good ones, and I'm not truly able. Now mind that this thing, this is a good choke, that this thing is what? Those are the good ones, thank you. This thing, what you see here, is scalar product of phi ps phi, scalar product on the Hilbert space. That's exactly the semigroup. That's the meaning of the semigroup. So the conditional expectation is this object given the initial condition, you get ps phi, and then the product of the two expectation, that's integral, that's exactly the meaning of the semigroup. So that's it, okay. Now let me compute its Laplace transform. Mind, what I want to understand, if this guy, Et, increases faster, if this guy increases like t, then I have diffusive, at least I have a diffusive upper bound. If this guy increases faster than t, then I have a super diffusive bound, right? Because this gives you exactly the variance of the second component. I just want to understand what to expect just in terms of expected values or variances. Clear? Siva, is it clear what I'm saying? Yeah, good. So let me compute its Laplace transform. This is Laplace transform of that guy. I denote Laplace and Fourier transform both with a hat. Laplace, that's integral of e to the minus lt. Okay, let me not write down. This is Laplace transform of that guy you see there, and using this explicit expression and everything, this is equal to twice lambda to the minus 2 times integral e to the minus lambda t from 0 to infinity, e to the minus lambda t phi pt let me write instead of pt, let me write e to the TL, because that shows it more explicitly what I have. E to the TL phi dt. And what you see here is exactly the resolvent operator, because it's e to the minus lambda t times e to the TL integrated. Mind, L, the symmetric part of L is negative. So e to the TL is a contraction. So this integral does make sense. So I can put actually the integral inside. It makes sense as a Riemann integral on the space of operators. So no problem with what I'm doing, right? So altogether, so what you see here is the resolvent, what I call R lambda phi R lambda phi. Where R lambda is the resolvent. R lambda is lambda identity minus L inverse, which is a bounded operator. Because L is, okay, this is a bounded operator. It's clear to see that the operator bound of R lambda is at most, operator norm of R lambda is at most 1 over lambda. So this is a bounded operator. All are bounded. Of course, we are interested when lambda goes to 0, so that will not be bounded. It's not uniformly bounded in. Right? So we are going to speak about operators, about resolvents, about things like that. By the way, this formula here is just simple thing. So this is a convolution of t with that. This is a convolution, and Laplace transform of convolution is product of the Laplace transforms. So Laplace transform of the linear function is 1 over lambda squared. Right? So all boils down, mind that ET is linear if E hat lambda between quotes with a grain of salt, because you need South Tauberian inversion here, but assume Tauberian inversion holds. ET is linear of E hat lambda is asymptotically 1 over lambda squared at 0. ET is superlinear if this is larger in order than 1 over lambda squared, where lambda goes to 0. So everything boils down to understanding the behavior. So crucial, understand the asymptotic behavior of phi R lambda phi. R lambda is that resolvent. If this guy stays bounded as lambda goes to 0, then you have a diffusive upper bound. If this guy explodes as lambda goes to 0, then hopefully, if you know the power of explosion, you get a bound on the explosion of ET divided by T by a Tauberian inversion. Good. Now here comes a magic, a resolvent formula. Here is a formula. We spoke about teaching function analysis this at lunch. Who was there? He's not here now. Here is a formula which I could teach an introductory course. It's not taught. It's not taught, but it's elemental. So when you teach resolvent, and when you teach bounded operators, resolvents of semigroups, which is introductory function analysis, then you could teach the following formula. Okay, let me waste some time. If S start is greater than 0, right? Then, no, let me not waste time because it will take longer. Sorry, no, I don't. I wasted a little time now, but no, I come back to this. Here is a formula. Phi R lambda phi, and what I'm saying now is true in absolute generality. In absolute generality, so let L be minus S plus A, where S is S star greater than 0 and A equals minus A star. You may assume that these are bounded, or you may assume that these are unbounded. For bounded operators, what I'm writing down could be taught in an introductory function analysis course. Namely, this is equal variational formula to the supremum psi in the Hilbert space. And it's true in general Hilbert space, not in my Hilbert space. Take a general Hilbert space, take a general operator which looks like that, totally general everything, of twice phi psi minus psi lambda identity plus s psi minus a psi lambda identity plus s inverse a psi. So this variational formula is absolutely generally true. And if you want to recognize something you learned indeed as an undergraduate, think about A being 0. That means you have a self-adjoint positive semi-definite operator. Then its inverse satisfies this formula. Or think about lambda plus s like a strictly positive. Yes, think about lambda plus s like a strictly positive operator, because s is positive. If you add lambda, that is strictly positive operator, then the matrix element of the inverse will be defined by this supremum. What you see here, up, down to here, so if you forget about this, take A equals 0, there's nothing else than taking some variational formula for a quadratic function. Okay, this is homework. Lambda identity. Right? This is full generality. Actually, it doesn't appear in books, and I learned it from, Varadan, Seturaman, some papers back, not very old papers, so say 10, 15 years old papers, but if you look how to prove it, it's indeed an elementary fact. Yeah. Now let's see what we can say. Diffusive upper bound. I'm curious in diffusive upper and super diffusive lower bounds. Clearly, if you just forget about the last term, which is a negative term, then you get an upper bound. Right? Then you get an upper bound. So you get phi r lambda phi. Let me leave some space for limit when lambda goes to infinity, goes to 0. Phi r lambda phi is certainly less than or equal to that supremum, but with a equals without the last term. But what I told you, that supremum without the last term is actually phi lambda identity plus S inverse phi. Which is what? Which is the resolvent of the symmetric part. So this formula, if you wish, the morale is that the diagonal matrix elements of the resolvent are bounded by the diagonal matrix element of the symmetric, the resolvent of the symmetric. Elementary, all physicists know this. Unfortunately, mathematicians are not taught these sorts of things, but physicists know it well, and that's how they have good intuition about what to expect and what to do. Right? Now, if it happens, and from here what follows? The limit when lambda went to 0, this limit gave me the diffusive constant, the asymptotic variance of xt divided by its square root of t. The limit of this guy, if finite, is exactly the asymptotic variance. Again, take it with a grain of salt because there is some tau variance. You have to be careful. I speak about Laplace transforms rather than, but these can be handled. So this gives the right-hand side, when lambda goes to 0, gives you the asymptotic variance of that integral.
So you can come back from the Laplace transform.
It's not totally trivial, but just take it with a grain of salt. That's the philosophy I'm saying, and you can do more than that, right? What do we get on the right-hand side when lambda goes to 0? Let's leave lambda go to 0. Limit or lim sup when lambda goes to 0 will be less than lambda goes to 0. This is S inverse. S inverse is, in my case, is Laplacian inverse. But let me write it minus S inverse. Now, first of all, formally, this is exactly the H minus 1 bound I told you in the beginning about the random walking random environment problem. But that's only a formal thing. If you think about this more probabilistically and not formally, what you see here is the following. Let me explain what you see here, because this is what. Think about it in terms of some process. I tell you, let's say take the random walking random environment case. I have my field. What you see here is the variance, the asymptotic variance of what is called random walking random scenery. Take an ordinary random walk, which is not influenced by the environment, and integrate phi along the trajectory of this process. So what's written here is equivalent to the following. I write it there. What's written here is equivalent to the following. Expect 1 over t, or the limit lim sup when t goes to infinity of 1 over t of integrate from 0 to t phi eta s ds squared is dominated by expected value, the limit when t goes to infinity of integral from 1 over t. Is there, yes? Okay, I'm tired now and I forgot to put things. 1 over t expected value integral from 0 to t. Now instead of phi of eta s, what was phi of eta s? I put it is tau x phi of, I put it explicit, tau s, tau xs omega ds. Right? That was, so shift your environment according to the process and look from the stage. It's a complicated thing because xs itself is determined by omega. But what you will see here is phi tau, I put here a ys omega squared, where ys is a ordinary, simple, symmetric random walk driven by this infinitesimal generator. Is it clear what I'm saying? So that the variance of this function phi integrated along my complicated process trajectory is dominated by the variance of the following process. Take the same random field on ZD, take an ordinary random walk independent of that random field, and integrate the random field you see along the trajectory of the ordinary random walk. Right? And this is due to the fact that the symmetric part of the infinitesimal generator is the same as the infinitesimal generator of what we call random walking random scenery. That means your ordinary random walk goes around and you record the scenery seen by the random walker, which is a much, much simpler object. And I'm able to compute this guy, but I'm not able to compute that guy. And this guy will be finite in 3 and more dimensions, if your field is essentially like IID or not very strongly correlated, if your correlations of your field are not very strong, then this integral, then this process will be diffusive. The process you see here in the integral is diffusive in 3 and more dimensions and super diffusive in 1 and 2 dimensions. This is just elementary computation. That's why in 1 and 2 dimensions, this doesn't give you a finite upper bound. In 3 and more it gives, and that's why the H minus 1 holds. Right? And similarly, for the other more complicated object, I have something very similar, and that's very strange. That take this random Gaussian field I just defined, take an ordinary random walk which goes along and integrate the field along the trajectory. The variance of that guy will dominate the variance of what I'm curious about. And that's why in 3 and more dimensions I get diffusive upper bounds and not in 1 and 2. And is it about time to finish now? Or how is it? Yes? So I didn't tell you much, so I am on page, I'm on page 14 of 19. So, but I don't think it makes sense to start now. But anyway, before finishing for good. So this gives you what to do, tells you what to do. And now, that tells you what to expect. So namely, when this guy, you have an upper bound like that, then you expect diffusivity. When you don't have an upper bound like that, or this upper bound is infinite, so it's not informative, then try to find elements from a well-chosen subspace. And that will be lower bound. That will give you lower bound on the variational formula. The well-chosen subspace will be the space linearly spanned by the translates, all translates of omega. So some sort of in a sort of Wiener chaos, the first subspace of a Wiener chaos, and it's heavy analysis. So it's not that it comes for free. What I'm doing, but in the first case, when you have an upper bound like that, then find a martingale approximation, which is again not for free, and there is some new theory there, which I will speak about in Calcutta, sorry, and for the random walking random environment story. And the super diffusive case, there is very heavy analysis here, which will give you indeed the super diffusive lower bound. But once this guy doesn't give you a finite upper bound, doesn't imply that this one is not finite. So still there is work to be done. But it can be done in cases, and I think it's time to stop now, so thank you very much.
More questions? One maybe a silly question.
There is no silly question.
Eta t of x, but you use only eta t of 0.
Yeah, but 0 is always, 0 is where I am. In order to know eta t is 0 1 minute later, I have to know eta t of x now all over, because 1 minute later I could be anywhere. So it's indeed I only use eta t of 0, but eta t of 0 doesn't evolve in an autonomous way. In order to see eta t of 0, you have to eta t of x altogether for all x's evolves like a Markov process. So in order to know what happens at eta t of 0, you have to understand the process eta t, which is eta t of all x's. So you're right, but on its own it doesn't say much.
What is the difficulty in doing it from the general state? So you have the initial, you said the initialization is required. So
that's a question everybody asks, of course. So how if you more okay the more.
Is it to do with knowing about convergence of this Markov process to this station?
All the techniques I have are Hilbert space techniques, and the Hilbert space story makes sense in the stationary setup. If you are not in the stationary setup, then it doesn't make sense to ask about operators or in that Hilbert space. That Hilbert space is the L2 space over the stationary measure. Right? And if I'm not, I can do things, I can do this type of function analysis in Hilbert space and not otherwise. That's a drawback. That's a very serious drawback. So I can't speak, in this theory, I can't speak about quenched results, only about annealed results. In Kolkata, when I speak about the random, only reduced to random, this talk was a sort of general survey. That's why I couldn't go to the end, because it was too much somehow. There I will concentrate only on the random walking random environment, and I do have quenched results, which use elements from here, but there is more there. Because this L2, this Hilbert space is for stationary.
Like, let's say you show super diffusivity. Is there an intuition of how the walk does it? Is it like it goes fast, some environment place hangs around there, goes a little further up? Is it like,
It's difficult. I have either to say I don't know or to sort of lie. Which one you choose?
The lie.
So I have some pictures. In some cases, for this Manhattan, for example, we have a fresh paper about this random walk in the Manhattan, which we knew for about 10 years ago. We knew the proof, but with Bennett Valco, but we were lazy to write it down, and now we were sort of forced to write it down, so we have a fresh paper. And there we have some computer simulations, and what you see is indeed totally different behavior. I mean, when it's much super different, it's power law super diffusive. When it's only logarithmically or log super diffusive, then of course you don't see much difference. But when there is a power law, then indeed you see totally different type of trajectories. Of course it's not ballistic, but it's a totally different type of trajectory.
You choose the environment that gives us how do they get the super diffusivity? Because the environment kind of pushes in one direction, is that?
It's not the case that it goes out in one direction, that it has an asymptotic, it doesn't have an asymptotic direction, if that's your question. No, there is no asymptotic direction. There is no asymptotic direction, but so what you see in the simulation is a totally different behavior. Even in the one-dimensional is better understood. Then you have the time to the 2/3, right? In my old paper, I've seen many simulations of that. Indeed, it goes far away, then goes back far away. So it behaves totally different. The local regularity of the process we constructed, I speak of the one-dimensional process now. It's locally more regular than Brownian motion because it moves faster. Locally more regular, and globally it's more diffuse, more dispersed than Brownian motion.
Is there a stochastic PD for eta t?
That's a very good question. So I can write down something like a stochastic PDE for you, and it would be good to understand in terms of stochastic PDE what it does. So let's do it maybe in the break or tomorrow morning. It's not a stochastic PDE in the classical sense, but it's something like a stochastic PDE. Yeah.
Omega is really a space of distributions.
Yeah. No, you are right. So I can write down something in a one-dimensional case. I can write down something. Don't ask me to do it now because I need a bit of concentration. I don't have formula written down now. But I've discussed this with people. Last time with Massimiliano Gubinelli about exactly this, whether we could do a stochastic PDE sort of thing on it. It's interesting. Might try. Yeah. I'm not good. I don't know enough about stochastic PDEs to do it myself. So.
How did you guess the Gaussian?
That's psychology, isn't it? I knew the one-dimensional for a long time because you asked about, time ago you asked about how the W function enters into the story. The W function enters into the story in such a way that the gradient of local time process, the gradient of local time, so difference of local time, behaves like a sort of discrete Gaussian, where in the exponential, instead of x squared, you have, I think, some of the wx's, I don't remember now the story exactly, but there are some formulas like Gaussian formulas for the discrete. So I had some feeling about this, and once I simply realized that, look, let's try this one, and then I started to do computations with Pierre Tarrés. First we did some wrong computations, and we got a result which was contradictory, and next day we realized that there was a mistake there, and indeed the Gaussian is good. So I don't know, that's difficult to answer. So once you get intuition about this, because it's indeed a surprise, why? This is a complicated process, why should it help? There is a nice balance between, but that's hindsight. First intuition comes. Yeah. So I didn't answer well, I know I didn't answer you, but once you understand how things behave and what to try to do, then maybe. Yeah. By the way, on the lattice, we also have on the lattice. It's instead of a Gaussian, we have what they call gradient Gibbs field with some gradient on the gradient. So how do they call it? Gradient Gibbs fields or something like that. I can show you later if you. Thank you very much.